today, I think the best thing to do is go over a lot of epsilon delta definition problems with continuity, because looking at that practice final your professor sent, it seems like you're gonna have to do a lot of epsilon delta proofs for uniform continuity. So I mean, if you don't understand continuity, you're not gonna understand uniform continuity. So today, I guess the goal is for everyone to understand like continuity. So is everyone good with the goal today? So okay, so let me go to the questions. Give me a moment. So, okay. So let's start. So share screen. So hopefully you all see my screen right now. So, right. Okay. So let's start off with like 17.4. Let's prove, we are continuous on 0 to infinity. Yeah. So, problem is I don't want to. So let's exclude the 0 case. So let me just say, let C be in 0 infinity, like I guess the open interval, right? So let's show it's continuous here. Yeah, let's make the 0 case like something else. So 1 to show root x is continuous at C. So let's just write out the definition. It means for all epsilon bigger than 0, there exists delta bigger than 0, such that x minus C is less than delta, implies root x minus root C is less than epsilon, right? Now, again, this should be open. Now, how are we going to do? So again, the attack is always relate this with this. So how are these two related? Can anyone tell me? Right, again, so let epsilon be bigger than 0. The point is you choose delta, right? So you have control over this. The point is that you want to make this small, provided you can make this small. So does anyone see a way? How do I relate root x minus root C to x minus C? Anyone? Yeah, it's a factor, right? So recall the great formula given by this, right? So x minus C is just root x. So root x minus root C and root x plus root C, right? So you sort of see, scratch work. What do we get? Root x minus root C is equal to x minus C divided by root x plus root C, right? So, and then, is everyone clear with this? And now I could just bound this by over roots, right? Because here, if I divide by something smaller, it's bigger, right? Okay, I have control over x minus C, right? Okay, I have control over how small this can be. So if I want this to be less than epsilon, what should my delta be? Anyone? So I want this in the end to be less than epsilon. So what should my delta be? This should not be that hard. Yeah, square root c times epsilon, right? So once you see this, choose delta equal to square root c times epsilon. Then, right, such that this is the if. Then, if x minus c is less than delta, which is root c times epsilon. From the scratch work, we have, c is less than or equal to x minus c over root c, which is less than or equal to root c times epsilon over root c, which is epsilon, right? Sorry, this should be, doesn't really matter. It's less than or equal to, right? And then we're done. I mean, for the case where c is between 0 and infinity. Okay, okay, now my question is, why did I assume c is between 0 and infinity? Why can c not be 0 here? Anyone? Square root of 0 is 0. That's perfectly fine. In fact, the 0 case is super easy. But in this, I mean, we have to show it for every point on 0 to infinity, right? So we have to let c be arbitrary here. But it's right here. You can't divide by 0. Yeah. So we sort of need a separate case, but the case for 0 is much easier. So let c equal 0. Then let's write out our statement, right? Want to show root x continuous at c equals 0. So in our case, for all epsilon bigger than 0, there exists delta bigger than 0, such that if, in this case, x minus c just becomes x, right? Because x minus 0. But in this case, really, I write absolute value, but really, like, root x cannot take negative values, right? So you might as well just write x bigger than 0. But then what is root x minus, what's root 0? It's 0, right? Then this is less than epsilon, right? In fact, I don't need the absolute value here, but let's just keep it there. So this should be clear. What should delta be? I mean, delta should not depend on x. So there should be no x for my delta. So I hopefully you meant square root epsilon, not square root x. So let's let delta equals square root epsilon. Then, here my x is positive, right? Because root x takes value. So this is just equal to, then if root x is equal to x is less than root epsilon, then, actually, let me think. We want square root, right? So it should be epsilon squared. Sorry. I think you reverse the operation. So if x is less than epsilon squared, then root x is less than epsilon. Yeah. And then you're done. So is everyone clear with this? The 0 case is simple, but you have to consider it separately. So, okay, great. So let's continue. Let's do more. So 17.10. I'll do the first two for you. Yeah. F of x is 1 for x bigger than 0. F of x is 0 for x less than or equal to 0. And we want to show it's discontinuous, right? So one for x bigger than 0, let me just write it like this, just to make things nicer. 1 for x bigger than 0, bigger than 0. It really doesn't matter, but x less than or equal to 0 is 0. Yeah, so it looks something like this, right? So hopefully by picture you are convinced this is not continuous at 0. So let's show this using epsilon delta definition, right? So if f was continuous at 0, then by definition we have for all epsilon bigger than 0, there exists delta bigger than 0, such that if x minus 0 is less than delta, this is just absolute value of x, then f of x minus f of 0, right? I'll write the whole thing out, but is less than epsilon. But you know, f of 0 is 0 in this case. So this is just f of x, and this is just x, right? So this has to hold for all epsilon, right? So if we are assuming it's continuous, this thing holds for any epsilon. So in particular, it should hold for epsilon equals a half, right? So when epsilon is a half, if we assume it's continuous at 0, there exists delta bigger than 0, such that if absolute value of x is less than delta, then f of x is less than epsilon. Okay, so how are we going to derive a contradiction? How am I going to get a value, right? So this just means that x is in, you know, negative delta to delta, right? So this can't be true, right? Because, sorry, epsilon is a half here. So you can write a half. Hopefully that makes things more clear. So here you see this can't be true, right? Because this interval, take, you know, delta over 2, for example. This element, you know, delta over 2 certainly is in this interval, right? It's in here. But f of delta over 2 is what? From your graph, delta over 2 is a positive number. So it's 1, right? Which is not less than a half. So not continuous at 0. Right, we have a contradiction here. Is everyone clear with this? Let me see. Okay, so let's do the next one. So let me just write it. So b, g of x is sine of 1 over x for x not 0, and 0 for x equal to 0. This is equal. Okay, so why is this not? So this function, in case all of you don't know, is very bad. It goes like, and then something like that. Yeah, infinitely many times. This keeps going to 0, but the waves keep getting like thinner and thinner, if you like. So what we're gonna do here is, turns out, so again, assume g of x is continuous at 0. Then what? So again, then it means for all epsilon bigger than 0, there exists delta bigger than 0, such that if absolute value of x is less than delta, what is my function here? My function is sine of 1 over x minus, at 0, it's 0, right? So minus 0 is less than epsilon. Okay, why is this not the case? Well, if this holds for all epsilon, it turns out epsilon equals a half also works in this case. So, right, then there exists delta greater than 0 such that absolute value of x is less than delta. Sine of 1 over x is less than epsilon. So the idea is I have to be epsilon away from 0, right? But you see here, we always reach 1, right? Sine always reaches 1. So the idea is like, and similarly -1. So you could choose like any point here, and you're gonna get that, you know, as you approach 0, you're gonna hit 1 and -1 infinitely many times. So you're not gonna be close to 0. So the idea is, okay, well, if the absolute value of x is less than delta, you know, the best thing to do is Archimedean property says there exists n in n such that 1 over n is less than delta, right? So why do I like this? So why do I use Archimedean property? It's because I need to get 1, right? And I know sine of pi over 2 is 1. But I need to make it small enough, right? So in particular, 1 over pi over 2 plus 2 pi n. This thing certainly has a bigger denominator than this, right? I mean, I'm multiplying by 2 pi. And then this is less than delta. So this term does belong here, right? So, right, it belongs in this interval. But what is sine of 1 over x in this case? Right, so sine of 1 over pi over 2 plus 2 pi n. This is just sine of pi over 2 plus 2 pi n, which is 1. And I mean, in this, sorry, I keep writing epsilon. This should be a half, right? Because epsilon is a half. And this is not less than a half, right? So the idea is you have to be 1/2 away from 0, but I can always choose points close, you know, multiples of, I guess, pi over 2 plus 2 pi k, such that I'm 1 away from 0. So it can't be continuous at 0. Is everyone clear on this? Hopefully you're all clear. Okay. So great. So let's go to, you know, so basically, don't think just because there's like a 1 over x, it's not continuous, right? So there are cases where we are continuous. You know, example, something like this. So why is this continuous at 0? To be continuous at 0, the limit as x goes to 0, you know, what does it mean to be continuous, right? It means this, right? Right. So here you see that this is true, right? In this case, because limit x goes to 0 of this term, this is bounded by squeeze theorem, just x, because sine's bounded by 1, and negative x, right? Because sine is bounded by -1. And these two go to 0, so this thing goes to 0. So this function is actually continuous at 0. Yeah. So don't think just because, you know, that the reason is not that 1 over x. It's just, you know, it's just that sine of 1 over x without anything else is a really ugly function.
I have a question.
Yeah.
So you use Archimedean property in order to show that the number you choose can be arbitrarily small, right?
Yeah, pretty much.
So you choose an n,
Mm-hmm.
and you formulate so this guy, which is even less than 1 over n.
Mm-hmm.
So this guy could be arbitrarily small, right?
Yeah, but I
Is
just need
this what
1
you
point.
mean?
I mean, so here it says, if epsilon is delta, any point satisfying this has to satisfy this. So to show it is not true, I just need to find 1 point that has absolute value less than delta, where this part isn't satisfied. So I chose this point.
So how you gonna set your delta?
No, we assumed it was continuous, right? So this is continuous. For all epsilon greater, there is a delta. So okay. So if it holds for all epsilon, then choose epsilon as a half. Then since we assume it's continuous, there is some delta such that it's true, right? I mean, I don't know what the delta is, but since I assumed it was continuous, I know there is a delta, right?
Right. Yeah.
Yeah. Like, I mean, that's all I need. I just need that some delta exists.
Okay.
Yeah. Okay. Any other questions? Yeah. I mean, this thing. I mean, you could choose something else, right? You could choose like, 5 pi over 2 plus 2 pi n. I mean, it doesn't matter. I just need 1 point. So, and the reason for the n is the nice thing is n is a natural number, right? So, if it wasn't, the reason I couldn't do it is because pi over 2 plus something irrational might not be 1. Like you don't know what it is, right? I mean, we only know like sine for like some really special values of like multiples of pi. So, okay. So let's go over 17.12. So a f continuous real valued function with domain AB. Oh, okay. Yeah. So want to show, so basically we have that f of r equals 0 for, yeah, let me see if I copied it correctly. Yeah, f of r is 0 for all r and for all rational r. For all rational numbers are in AB. Show f of x equals 0 on AB. So this is the nice thing about continuity. Yeah, so information about, your function on rationals basically tells you, a lot about points nearby. Okay, why is this true? This should actually be really quick. So we know what do we need right now? We know it's 0 on rationals. So what's left? We need to show it's 0 on irrationals on AB, right? So let C be an irrational number on AB. Okay, what can you tell me about how can I relate an irrational with a rational? What do I know about rational numbers? What's the nice thing about rational numbers? So anyone? This is pretty important. So basically I'm asking, can you find a sequence? Is it always true given an irrational? There's a sequence of rationals going to it. Is that true? Yes, right? So I know there exists rationals. I'll call it Rn going to C, right? where, I mean, I mean, if C is an AB, I could certainly make this an AB. But then you are done. Because what does continuity say? Continuity, since F is continuous, they gave us it's continuous. We have that limit n goes to infinity Rn is the value of the function, right? F of C. But what is F of Rn? What is F of Rn? So what did we, what's the assumption here? Rn and Q. These are rational numbers. So what is F of Rn? Yeah, it's 0, right? It's so this is just limit n goes to infinity of 0. So F of C is 0, right? And then C was arbitrary, irrational, so we're done, right? So F of X is 0 for all X in AB. Yeah, everyone clear on that? Great. So the second part is really simple. So let F, G be continuous real valued functions. This is a one-line proof now on AB, and F of R equals G of R for all R rational in AB. Show F of X equals G of X for all X in. So, I mean, I'm not going to do this because it's one line. All you do is just, I mean, this is the same as saying F of R minus G of R equals 0 for all R rational in AB. So, you just, if you call this part A, just apply part A to the function F minus G, right? And then you're done. So, right, because if F is continuous, G is continuous, the difference is still continuous. So, okay, everyone good so far? Yeah, so basically saying if two functions agree on rational numbers and they're continuous, they're the same function. Okay. 17.13. Okay, let's do more epsilon delta proofs. So 1 if X is in Q, and 0 if X is not in Q. So this function is really bad. So this function, show F is not continuous for all X and R. So this function is discontinuous everywhere. So let's sort of see, why. And if you wanted to graph this, it's impossible, right? Because I mean, it'll just be like, you could try drawing dots, like dot at 1, dot at 0, but like, it's kind of impossible to graph this. So that's how, wild this function is. So again, if you think about it, you should separate this to the case where, let's show it's not continuous on rationals, and then let's show it's not continuous on irrationals. Yeah, so let's let C be in Q and assume F is continuous at C. Right, then for all epsilon bigger than 0, there exists delta bigger than 0 such that if X minus C is less than delta, what is F of X? What's F of C in this case? What is f of c? Yeah, it's 1, right? So hopefully it's clear what we need, right? How, I mean, let epsilon be equal to a half. Then I mean, since we assume it's continuous, then there exists delta bigger than 0, such that if x minus c is less than delta, f of x minus 1 is less than a half. So why is this a contradiction? Again, this means x is in c plus delta, right? So why is this a problem?
Because f of x can always be 0, no matter what range you choose.
Yeah, I mean, delta is fixed now, right? So we, there is a delta. So yeah, basically, there is choose an irrational in this interval, right? Choose irrational. I'll just call it R. And then f of R minus 1 is 0 minus 1, which is 1, which is not less than a half. Yeah. So that becomes a problem. Okay. Is everyone good? Okay. So let's continue. So that's case 1. So now we're gonna let C not be in Q, and the proof is the same. So assume F is continuous at C. Then what? Same thing, right? For all epsilon bigger than 0, there exists delta bigger than 0, such that if x minus c is less than delta, f of x minus, so in this case, what is f of c? So c is an
0.
irrational. Yeah. And hopefully, it's the same thing, right? Epsilon is a half, then there exists delta bigger than 0 such that less than delta implies f of x is less than a half. And it's clear, right? Because again, this means x is in c minus delta, c plus delta. So you choose a rational R in c minus delta, c plus delta, then f of R equals 1 is not less than half. Yeah, so not. Is everyone good on this? Okay, great. So hopefully there's no text. Okay. So, let's move on. So, let's, I'll do part of B for you. Yeah, so just part of it. So let's let h of x be x for, for rational numbers x, and h of x equals 0 for irrationals. So, h of x equals x for x in Q, and 0 for, so by the way, before I continue, there's no reason why, I mean, epsilon was a half, right? In this case, you could see that epsilon being like a third, I mean, even epsilon being 1 works, right? Because you get 1 is not less than 1. but like certainly not every epsilon will make this false, right? If you chose epsilon as 2, it's just always true, right? Because the biggest difference between 1 and 0 is 1. You'll always be less than 2. So yeah. So I mean, epsilon being a half is not something you have to choose, right? So you could have chosen like epsilon is 1 or a third or something else. As long as it works, whatever works for you. So let me just, show that it's, so the problem is show continuous at 0 and nowhere else. So let me just, do one of the hard parts. So let's see. Let's show it's not continuous on a rational without 0. Yeah. Why is that the case? So actually, let's just do everything. Okay. So here, okay. So what is the, so assume, again, the point is assume it is continuous. Assume it is continuous. Then what do we have? We have for all epsilon bigger than 0, there exists delta bigger than 0, such that if x minus c is less than delta, f of x minus c is less than epsilon. This is actually the easy case, actually, because what you're going to see is if this is true, continuous at c, I'm going to let epsilon be c. Hopefully you can see why, right? So then there exists delta bigger than 0 such that if x minus c is less than delta, f of x minus c is less than c. So basically, this is just means this, right? So what's the next step? Hopefully you all see this. What am I choosing my f of x to be? So I'm going to be choosing an irrational number, right? Choose r irrational in. Then what is f of r minus c? Equals 0 minus c, which is, let me be more clear. Absolute value of c, yeah. So, because c can be negative, so. Yeah, so this is absolute value of c, which is not less than absolute value of c. Yeah. So the reason I did this is because epsilon has to be bigger than 0. So I have to take absolute value. But other than that, hopefully it's clear. So that's the, easy part. So why is it not continuous on irrationals? So let's sort of see why. So C be irrational, right? So here, okay, so let's write out what the definition is. So this is a bit harder. So for all epsilon bigger than 0, there exists delta bigger than 0, such that if x minus c is less than delta, f of x minus, what's f of c? F of c is what? If c is irrational, f of c is 0, right? So it's just saying this. Yeah. So why do I like this? So the reason for this is, so let me just, so again, it's kind of unclear what epsilon should be, but the idea is, okay, this thing, if I'm going to choose a rational number, this thing is just x, right? And here, my delta, I could choose x as close to c as I want. So in particular, I can make it within like, c over 2, and then c plus c over 2. Yeah. So, okay. So what we're going to do is we're going to make the image between this. So we are going to let epsilon be, so this, you know, the reason I chose this is because I worked it out beforehand, but hopefully like you sort of see what's happening, right? This, my x is close to c, so my f of x is close to c. So if I choose epsilon to be some number away from c, like, you know, c over 2, for example, if I choose x small enough, it's close to c. So, you know, if you're close to c, you're eventually you're away from c over, you're bigger than c over 2, right? So that's the idea. So consider minimum of, I'm not sure if this is all necessary, but, you know, so in this case, oh yeah, never mind. Let me just write this first. So if it holds for epsilon, then it holds for, so there exists delta bigger than 0, such that if x minus c is less than delta, f of x is less than c over 2. Okay. Let me do this. I keep forgetting this. So absolute value of c over 2. So here, what we're going to do is I'm going to choose s to be the minimum of c over 2 and delta. So why is this the case? So if s is in here, then certainly what do we get? Choose q, rational q, in c minus s, c plus s. So question, why does q lie in here very quickly? So it lies in here because s was the minimum, right? So s was smaller than delta. So if I choose a delta ball, right, c minus delta c plus, since s is less than delta, s is just some smaller ball, right? This is c plus s, c minus s. Right, now, why did I do this? Well, because what's f of q here? What can you tell me about f of q? How big is it? You know, so c minus, so I'm asking, so if q is in here, right? So this is c minus s, c plus s. Q is something in here. What is this term bounded by? If s is smaller than, is the minimum of c over 2, this thing c minus s is bigger than or equal to c over 2. Agree? I mean, at least in, like, you know, absolute value. So this thing is gonna be bigger than or equal to, you know, absolute value of c over 2, and then you're done. So again, I chose the minimum to make, you know, I chose this to make this true, and I chose this, you know, so I lie in this interval, right? So hopefully that's clear. And then the easy part is easy, continuous at 0. So is everyone good so far? Okay, great. So this one, let's just show directly. Let epsilon be bigger than 0. We are going to choose delta to be epsilon. Then for absolute value of x less than delta, which is epsilon, what do we have? I want to show f of x minus f of 0, right, is less than epsilon. Want to show, right? But what is f of x minus f of 0? At 0, what is my function? At 0, I'm just the value, right? So it's 0. So it's just saying f of x is, you know, so this is just f of x. Now we have two cases, right? If x is if x is rational, so x, let me just write x in Q, then this is just absolute value of x, right? Because f of x is x, but we chose absolute value of x is less than epsilon, so this is less than epsilon. If x is not in Q, well, this is just 0, so it's still less than epsilon. So you are done. It's continuous at 0. So so before I end, let me just sort of tell you that you should try out for practice 17.14. It'll be a bit of a challenge. So it's something similar. So 17.14 is saying it's a bit hard to, yes. Okay, so 0 for irrationals, right? So f of x equal 0 for x not in Q. And this is a bit harder to write. So it's 1 over Q for x in Q. So what we mean by, what is this Q here? So if x is a rational, it's of the form P over Q reduced, yeah? And then we say like f of P over Q is 1 over Q. So by reduced, I mean like, you know, because a priori you have, you know, we're not, so we don't allow this, right? It's not 1 over 4. It's a half, because you reduce it first, so it's like 1/2, and then you do 1 over the denominator. So like f of, for example, 4 over 8 is not 1 over 8, it's a half, yeah. Like f of 2 over 6 is 1/3, yeah. So you always, and then similar, f of 4 over 6 is still 1/3, yeah, because you take the denominator. So basically, you should try this for practice, epsilon delta proofs. It's a bit harder, but the claim is that it's continuous on irrationals and discontinuous on rationals. Yeah. So just do that for practice. But hopefully everyone is clear on how epsilon delta proofs work. Make sure you are, because again, the sample final has epsilon delta proofs for uniform continuity. So, and to understand uniform continuity, you have to understand continuity. So, okay, that's all I have for today. So again, your quiz, all right, your quiz. Your quiz is on continuity, yeah. Yeah, you know, so I'll just tell you now that the multiple answer one is just, you know, multiple answer is just me giving you a bunch of functions. You know, I give you functions, and then you determine which ones are continuous. Yeah, hopefully that should not be hard. So again, I'm not gonna put epsilon delta, you know, stuff on the quiz. So, but make sure you practice it. Yeah. Okay. Sample. You mean sample final? I don't think there was a sample midterm. So from someone told me on the email, she's gonna go over it on review day, right? If you look at the calendar, I think there's like a review day. So, yeah. Okay.